Okay, there we go. So, organic molecules in chemistry relate to biology, which is when we talk about organic material in biology, we mean like the materials, the molecules that make up living stuff. Does that make sense? But if you've taken my biology class, and we've even mentioned it a bit in this class, what is the backbone of all of the molecules of living things? Is an example of one, but like what atom shows up all the time? Yeah, carbon. And if you're in my bio class, we talked about carbon. Why is carbon, first of all, what kind of bonds does carbon tend to make? Ionic or covalent? Look where it is. Can it share? Covalent. Yeah, but it's on the very poor side of covalent, right? In fact, it needs to make how many bonds to get a stable outer shell? 4. Which, if you're thinking about designing molecules to have like big shapes and structures, a molecule that can, an atom that can make 4 connections is very useful. Does that make sense? Because you can start to build 3-dimensional shapes out of it, up, down, left, and right, basically, right? So organic molecules are molecules made on a backbone of carbon and hydrogen atoms. They can and do contain other atoms, all right? But carbon and hydrogen are always the main kind of spine of these. Now, if carbon is useful because it wants to make 4 bonds, why is hydrogen useful? Because it only makes 1. So if carbon lets you start building in, say, a big 3-dimensional chain where the thing will just keep growing and growing and growing, hydrogen acts as sort of a cap. Because as soon as you make a bond to hydrogen, because hydrogen can only make 1 bond, that's where that chain or that's where that branch will stop. Does that make sense? So carbon lets you branch out, hydrogen lets you contain it, lets you have the molecule stop. Versus if you just let carbon grow with nothing to stop it, it will form crystals. Carbon can make a few different crystal structures. Does anyone know some of the crystal structures carbon forms? You're using one of them right now, most of you. Carbon dioxide is not a crystal structure. I mean, it can be, but it's a small molecule. But a big carbon molecule that's just carbon, nothing else. Graphite, coal, charcoal, diamond is just a big carbon crystal. But here, we don't let it just grow as just carbon. We use carbon to grow and hydrogen to constrain that growth. And with that in mind, we can kind of carve this into any shape we can imagine. Does that make sense? And you can make really big, complicated molecules with really big, complicated shapes. And then we can start adding other atoms into it to have those actually do things, interact with other compounds. And if you've taken biology, you've learned about DNA, and you've learned about proteins, and you've learned about lipids, and these different organic molecules. But at its most basic, if we make a chain from carbon, like this, every carbon wants to make how many bonds? And actually, we'll put it here. It wants to make 4. So we could potentially have a chain that is just 1 carbon, but if it's going to be only 1 carbon, what has to be connected to each of those bonds? Hydrogen. So it would look like this. Does that make sense? To have it only be 1 carbon long, by default, all of those would be filled in with a hydrogen. Hydrogen as opposed to fluorine or chlorine or bromine or something else that makes only 1 bond, because hydrogen is really plentiful. There's a lot of hydrogen in the universe. It's the simplest molecule. Altogether, what's the formula of this? How many C's? CH4. Yeah, we don't usually write a 1, so we'd say CH4. Now, if we were naming this with like the way we learn to name covalent compounds, we'd call this carbon tetrahydride, right? But the problem we're going to find is that these get... Is that like propane? No, but you're on the right track. But we don't name it that way. We actually have this naming system for organic molecules that is different, because we don't even want to ever bother mentioning that there's hydrogen, because we assume there's hydrogen. Hydrogen fills in the gaps. So a naming system is based on chains of carbon. Does that make sense? And if we have a chain of carbon that's one long, in other words, a single carbon atom with 4 hydrogens, we call this methane. Right? And this ane ending is going to tell us that it is a carbon chain. We call these alkanes. So if you see ane, it means a chain of carbon atoms. You don't necessarily need to write that because it says that above, but I sometimes find it helpful to write things more than once. Okay, so methane is 1 carbon. I'm not going to draw all of these because you'll see quickly that it gets a little out of control. But a carbon stuck to a second carbon would look like that. But again, how many bonds does each carbon want to make? 4. And in an alkane, we're only working with single bonds. That's important. We'll get to double bonds later, but we'll mention here that we're dealing with single bonds here. So what fills in each of these spaces? Hydrogen. Now, sometimes to save space, you'll see this written as CH3, CH3, where they just write the hydrogens in like that rather than drawing each one. These are both acceptable. What's the formula for this? How many carbons?
2.
And how many hydrogens?
6.
6, good. And does anyone know what this is called? Methane is 1 carbon. They got real creative here. Ethane. Yeah. Yeah. Okay. Now, if we did 3 carbons, CH3, CH question mark, CH3, we know the ones on the end are going to connect to 3 hydrogens. How many will connect to the one in the middle? Wouldn't actually hurt to draw this. Again, we're not going to draw them all. How many bonds does this middle one want to make? 2. So how many hydrogens on that middle carbon? Only 2. Right? It can't connect to 3 because it's making 2 connections to other carbons. So that would be CH3, CH2, and then CH3. What's the formula of that altogether? How many carbons? And H, how many hydrogens? 3, 6, 8. This one, you mentioned, this is in your barbecue. It's a gas at room temperature, but if you put some pressure on it, it'll actually turn into a liquid, a little bit of it. So sometimes in the tank of this, you'll hear some sloshing of a liquid in there. Yeah, this is propane. You'll also see this drawn sometimes like this. All right? This would be a proper Lewis structure.
Oh, sorry for the interruption, Mr. Lugo.
Yep. Yep.
Can I get your attendance, please?
Yep.
Thank you.
No problem. Hey, crew, can you get on that?
Oh my God.
Thank you. So that would be a Lewis structure. This is called a skeleton structure. And in a skeleton structure, they just use lines to draw bonds, and they don't bother writing C's. They would write any other, they assume that at the end of each line is a carbon, unless it says otherwise. Does that make sense? So if I wanted to put a nitrogen here, I'd draw an N, but otherwise we just assume at each corner is a carbon, and then they don't even bother drawing hydrogens. Because when you get to really complex molecules, there might be 100 hydrogens, so they just don't bother. Does that make sense? So we'll see that. What if we had not 3 carbons but 4? The first one, because it's on the outside, how many hydrogens would it have? This one's on the inside. How many hydrogens will it have?
2.
This one's on the inside. How many hydrogens?
2.
Great. This one's on the outside. How many hydrogens?
3.
Great. That's 4 carbons. How many hydrogens? Might notice the pattern. Yeah, very good. It goes up by 2 each time. Not that you need to memorize that. Methane, ethane, propane. This you might have in a lighter. Under a bit of pressure, all of this becomes a liquid. So inside your lighter, it looks like a liquid, but then as soon as you release that pressure, it turns into a gas, which is why we use it for lighters, because you can have it as a liquid in there. You press the thing, it comes as a gas. Keeps it safe inside the lighter because there's not much gas to explode, but you don't have liquid dripping out of it. Does anyone know what's in your lighter?
Lighter.
Yeah, which is butane. Very good. By the way, as a skeleton diagram, we would say there's a carbon, going up to another carbon, going down to another carbon, going up to another carbon. That's the skeleton structure of that. It is nicer, isn't it? Just real quick to draw. 1, 2, 1, 2, 3, 4. Yeah, well, I will tell you sometimes to draw a skeleton structure. It's a lot easier. In fact, starting here, we're just going to do that. How many carbons is the next one? C5. How many H's will it have? We've got the pattern down by now. 12. That'd be 1, 2, 3, 4, 5. Remember, it's not the lines. It's each vertex. It's each place where there's, you could imagine drawing dots here. You don't actually draw the dots in a skeleton diagram because that's too much work for chemists. We're lazy. But these are actually showing you the bonds. Does that make sense? And again, we don't even bother showing hydrogen because there's so much of it. It gets struggly. So we know what we call this. Now it starts using prefixes that will be familiar to you. There's 5 carbons, so we call this pentane. Yeah, that's right. Penta is the prefix, so we call it pentane. The next one would have 1, 2, 3, 4, 5, 6 carbons. On each of those would be 3 hydrogens, 2, 2, 2, 2 hydrogens, 3 hydrogens. So 3 and 2 is 5, and 2 is 7, and 2 is 9, and 2 is 11, and 3 is 14. So C6, H14, and now we're in predictable naming. Pentane, but this has 6, so it's going to be very good. The next one will have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that'd be 7. This would have 3 and 2 is 5, and 2 is 7, and 2 is 9, and 2 more is 11, and 2 more is 13, and 3 more is 16 hydrogens. Because again, remember, all those inside carbons can only hold 2, right? But the outside carbons can hold 3. What do we think we call this? Do you know the prefix for 7? You're really close if it were French-based. In Latin, they didn't call it septa, they called it hepta. That's right, but heptane. Very good. The French S is sort of a variation on that. But this one, you'll know for sure. When it's 8, octane. Very good. Which we think of as being gasoline. The truth is gasoline's a soup full of like a million different things. It's just petroleum distillate that's been broken down.
I don't know, say like moonshine.
Now, how would I draw the skeleton structure for this? We go up. How many carbons have I drawn so far? Say, in the worst case scenario, you're wrong. How many carbons would just that be? 2, right? 1, 2. Now I've drawn 3, 4, 5, 6, 7. That's right. Yeah, because each line represents a bond, right? 1, 2, 3, 4, 5, 6, 7. Oh, good call. 8. There we go.
Or just 3 mountains
and a slope. That's right.
Half mountain.
That's right. This one would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 4 mountains. And that'd be C9H. How many? 20. Very good. This one, if you have an Italian grandma, this is no name. Right? There you go. And finally, this actually does keep going. We're going to stop at 10 because you get the point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we would call this decane. All right. These chains of carbon form the backbone of most organic molecules. Now, they can actually get much longer than 10 carbons long. But we're going to start off dealing with relatively simple organic molecules. Does that make sense? So we're going to start with things that are on the small side, and we'll build up to bigger things. But this is the naming structure. But remember, the whole point of carbon is that carbon can make 4 bonds. So does it have to only make a straight chain? At any one of these, we could branch off and start another chain. Does that make sense? So we can branch. So if you look at this, here is a molecule that isn't one chain. It's a chain with some branches. Does that make sense? So the way they've drawn it kind of shows us how to think of it. You won't always see it drawn this neatly, but if we look at this drawing here, by the way, if I wanted to, I could draw this as a skeleton diagram. Let's try. How long is the main chain? 1, 2, 3, 4, 5, 6. Very good. So that would look like this, right? 1, 2, 3, 4, 5, 6. And then on the second carbon, we have a chain coming out. How long is that chain? Yeah, there's just one carbon coming off it, so we draw it like that. And then the third carbon has nothing. The fourth carbon has a branch coming off of it. How long is that branch? 2. So we'd go up 1 and 2. Does that make sense? So this would be the skeleton drawing of that same thing. And with a bit of practice, the skeleton drawings will become kind of intuitive for you. And you can see this is kind of a lot easier to do than that, right? Now, this I think is easier to understand, right? So early on, I'm always going to try and draw it this way, and then we'll mention the skeleton. We'll be like, hey, let's take a look at what that would look like as a skeleton drawing. When you get more comfortable with these things, you tend to just do the skeleton. Does that make sense? But it's weird to think like that's a chemical structure because it looks like just a bunch of squiggly lines or straight lines, right? But right? But now let's talk. The main chain was how long, you said? 6 carbons. So what is the base of this molecule? This molecule is it's a hexane. So the main chain is the first thing we always want to find. And the main chain isn't necessarily going to be drawn straight. It's always the longest straight chain you can make. Does that make sense? Whatever the longest, I'm not even going to say straight, just the longest possible directly connected chain you can make. So it actually, there's another way we could draw this that would be just as correct. Because this is also a chain of 1, 2, 3, 4, 5, 6. And actually, if you look, this is the exact same molecule. Does that make sense? If we draw it this way, it's still a chain of 6. The second carbon still has a branch coming off of it that's 1 carbon long. And then the fourth one has a branch coming off that's 2. Does that make sense? So these are both fair ways to draw it, but this is obviously the better way to draw it because it's easy to follow. Does that make sense? But sometimes you will find sneaky ones where, it's not obvious where the longest chain is. When in doubt, just count it. Does that make sense? The longest straight chain you can make is the best thing to call the primary chain. It doesn't really matter. You can use the wrong name for something, the quote-unquote wrong name, and as long as it's still accurate, somebody will still be able to make the molecule. Does that make sense? But the point of naming here is it's going to be descriptive. So in this case, the longest chain is 6. So this is a hexane, right? But then what is this group? How long is this chain? So we would call it normally a what? Methane. But to say that it's a branch, instead of calling it methane, what we say is that it is a methyl group. Does that make sense? Yeah, because H3 so YL tells us that it is a branch. So if it's the main chain, we keep that ane ending. Does that make sense? But if it's a branch, we just change the ane to ill. In other words, we just say, oh, this hexane, this 6-carbon chain, has a methyl group on it. Well, with that in mind, then, what would we call... Oh, I already heard it. Look at that. What would we call this chain? That was a poorly chosen color. Ethyl. That's right. Very good. So now... Yeah. Okay, now we give a little more information here because this isn't just a methyl group. It's a methyl group that is on a specific carbon. So here's the thing we do. On our main chain, we just number it. So on our main chain, this would be carbon number 1. This would be carbon number 2. This would be carbon number. This would be carbon number. This would be carbon number. And this would be carbon number 6. Okay. By the way, you could number it the other way too. we'll talk about which way to choose. But usually we draw our diagrams from left to right. That's usually kind of considered the polite way to draw the diagram. So if they've given you the diagram and they've done a polite job, it should be numbered left to right, but it won't always be the best way to number it. We'll talk about that. Basically, you want your numbering to be so that you end up with the lowest numbers possible. But if you look here, this methyl group, what carbon is it attached to? It's attached to carbon 2. So we'd call this a 2-methyl group. Does that make sense? In other words, we're saying take a hexane and on carbon number 2, add a methyl group. And methyl just means how many carbons? No, methyl means 1 carbon. And then ethyl, this would be 4-ethyl. Does that make sense? And so the name of this abomination is just all of this information put together. Does that make sense? And we work, I'm going to show you the order we write it, but I always start by writing the main chain, but I leave myself space because we actually have to kind of work backwards. The main chain is a hexane. And eventually you'll just write it, but for now, write the main chain first. And then these go not after it, but in front. And we put them in alphabetical order. That's just the rule. For anything that goes in front, we just, hello. Notice right here, my friend.
Already gone.
Okay. Oh. So these 2 groups here, we're going to put in front here, and we're going to put them in alphabetical order. Does that make sense? So which one do we put first? What comes first, ethyl or methyl? Alphabetically. Ethyl, yeah. Just follows the alphabet, all right? So we would call this 4-ethyl, 3-methyl hexane. Did I say 3? I meant 2. And then I'm going to erase it and rewrite it so it's neat. So we start with 4-ethyl, and we put the dash between them. It's lowercase. And then we say 2-methyl, and then we say hexane. This is a single word. 4-ethyl, 2-methyl hexane. Now, I'm not saying you should name your first child that.
I am.
You know, does 4-ethyl, 2-methyl hexane high have a good ring to it? I think so. You could call him Methy for short. I guess Methy High might not be a great name. Methy High might be a problematic name. You should actually avoid meth as a prefix in any of the names of your children if you're going to keep High as their last name.
I feel like you could have just erased like the hexane at the first one you wrote at the beginning, and then you didn't have to, redo the whole entire thing because you could have gotten out the way and wrote it nicely either way. But also, calling that beautiful chain right there an abomination, it's giving Miguel O'Hara when he called
Okay, you stop. Okay, stop. Okay, over here I just wanted to make a little box. Let's just try another one. Let's see if we can draw 2-methyl butane. Just take a minute and try and draw that. See if you can break it down. And if you look here, the name at the end tells us how long the main chain is, right? That's what we saw here. And then the thing at the beginning tells you about any chains that are added to it, any side chains, branches. So see if you can draw 2-methyl butane in this space down here. 2-methyl butane. So would you also, yeah, would you do me a favor and cleaning off my hands? Just all the way around. And there's a spray cleaner somewhere at the back, a little blue bottle. And the thing I always use a lab coat. It really comes off great. Lab coat and wash.
Wait, don't.
No, take your time. Take your time.
So does it always start up or down first?
I always start by going up. It actually does not matter.
Okay.
It does not matter. There's no rule. In fact, I'm not going to draw this as a skeleton diagram first, though you're welcome to. I'm actually going to draw the C's and H's.
Well, I mean, like I just found.
Yep. No, the skeleton diagram, much easier. This one here, how long is the main chain?
4.
Yeah, that's 4 carbons, right? So we go, okay, carbon, 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 carbon. How many H's will be on the first one? It's on the outside, so
3,
yeah. And on this one?
2,
Yeah, and this one?
2,
And this one?
3.
Okay. And now it says, so that's our butane. And then this isn't just butane, it's 2-methylbutane. So what's a methyl group?
So it is 1
One carbon. And where am I putting it?
at the second carbon.
Yeah, the second carbon. So I'd put that there. And how many H's will this have? Yeah, because it's only making one bond, right? And if you did want to draw that as a chain diagram, we could just go 1, 2, 3, 4, and then one up here, right? That would be our main chain, and that would be our methyl group. Does that make sense? How's that feel? Not too bad? This may seem clumsy, but you actually quickly discover it's a really much. I mean, this thing, if you wanted to name it conventionally, well, you could count the carbons and say altogether there's 1, 2, 3, 4, 5 carbons, and there's 3, 6, 9, 11, 13 hydrogens. So you could call it, hexacarbon, I don't know how you say 13, actually, trideca maybe. Doesn't matter. The point being, you could call it that, but that would just tell you how many carbons are in it. This name doesn't just tell you how many carbons are in it, it tells you how it's put together. Does that make sense? The name gives you the shape of the molecule, which is actually the goal. In fact, this name can only correspond with this molecule. So like if I went to moleview.org, which I love, and type this name in, it's going to give me this molecule. If the internet in here worked, which of course it never does. What's streaming speed? I'm getting decent streaming speed.
Close out some tabs and see if that would...
No, my computer is not the issue. This computer is a workhorse. It's got loads of capability. Well, we'll come back to it. Okay, so one thing to know is that you can have the same side chain appearing a couple times. Two things I want to note. The first thing, if you look here, they've numbered this 1, 2, 3, 4, 5, 6, 7. Why did they start numbering over here? We always number so that we work with the lowest numbers we can. Does that make sense? If I number this way, my first branch happens on carbon 2. If I were to number it this way, I wouldn't get a branch until carbon 3. So we prefer the method that gives us lower numbers. The truth is, they'll both be good names. This one's a better name.
So, okay, for the next one, does it matter?
So this one, we can either be on carbon 3 or we can be on carbon 1, 2, 3, 4.
Oh.
So we're always going to go this way because it'll give us carbon 3. Now again, this is kind of bad manners to draw this way because usually we try to draw things for people so they can label it left to right.
Bonds, I don't know, would be the same. And then would it matter where?
Well, if you look here, this one tells you that you could call this the main chain or you could call that the main chain. The reason we don't call this the main chain is because then we'd have a branch, and what would there be on the branch? Another branch, which you can name, but it's a pain. So this is the better main chain because we get no secondary branching. Does that make sense? So that's our main branch. How long is that? 7? So what's this thing? It is a... What's 7? It's a heptane. Okay? But it's got this group on it here. Well, that's a terrible color choice. It's got this group on it here. What would we call that group? That is a methyl, and specifically it is a 2-methyl. Good. What about this one? It's a methyl again, but this one is a 3-methyl. And what about this one right here? What is it? It's a 5-methyl. And finally, we've got, in addition to that, this group here, which is a 1, 2, 3. How long is that? What's 3 carbons? Methyl, ethyl.
Propane.
Yeah, so this would be prop. Yeah, and what carbon's it on? 4. Okay, so first of all, alphabetically, what am I going to put first? The methyls or the propyls? Methyl. Now, could I call this 2-methyl, 3-methyl, 5-methyl, 4-propyl heptane? I could, but I could, and that wouldn't be wrong, but it would be embarrassing. You know, Trush would make fun of me. Because, and I'll show you it wouldn't be wrong. Like if you look here, if I put, what is it? 2, 3, and 5? 2-methyl, 3-methyl, 5-methyl, and then what's the 4-propyl? Oh, really? 4-propyl, and then heptane. I'm hoping that this doesn't just look in a library, but actually interprets the names. I bet it'll make this, though I bet the internet is so slow. So that isn't wrong. Watch, it's going to give us the molecule. How is it this slow? It's unbelievable. Well, we'll come back in a couple days and it will have built this. Infuriating.
How much?
But what we 64 gigs. I've got lots of RAM. I got. Did I? No, that's the beginning of heptane. So we're good. Anyway, while that loads, which it will, I promise, there's a better way, which is we just list them all at once. Does that make sense? So we have methyl groups on 2, 3, and 5. And now we just need to say that we have methyl groups on 2, 3, and 5. So this is a trimethyl. How many methyl groups does it have? 3. And where are they located? On carbons 2, 3, and 5. So 2, 3, 5, trimethyl. And then what else do I have to put on there? That propyl group, which is on carbon 4. So it's a 2, 3, 5, trimethyl, 4-propyl. And then what's the main chain? Heptane. That's the best name for this thing. The truth is you could actually give this a few different names that all work, that all follow the system, but this is the shortest possible name for this. It's the most efficient. It's the most, quote-unquote, parsimonious possible name for this. I'm going to see if I plug in.
What would be like the long?
Oh, there we go. See? So if you look here, did this make our compound? It did, right? And we have a carbon chain that's 1, 2, 3, 4, 5, 6, 7 carbons long, right? Do we see that? There's our main chain. And we have a methyl group here. I know that looks really long. It's just showing you the dimension, but that's 1 carbon there. We have 1 carbon there and 1 carbon there. So we have our methyl groups. And then we have 1, 2, 3 carbons here. So that is a propyl group. But the better name would be 2, 3, 5 trimethyl. Was it 4-propyl? Is that true? Propyl heptane. And that will give us the exact same molecule, but it's a much shorter name. See? And it gives us the exact same molecule. This, by the way, is what the thing looks like in 3-dimensional space. And you can see in 3-dimensional space, it's actually not that easy to see the chains, is it? Right? All the hydrogens really fill this in. So one of the things we often do is we just don't show hydrogens, right? Like, that maybe makes it a little easier to see, but
What was that German word?
Van der Waals spheres? Don't worry, we'll talk about. But there we go. By the way, one of the cool things about JMOL is that it doesn't look this up. For alkanes, it actually just generates the structure based on your names. You can always test your naming, because if you put it in here, it will give you a molecule. But JMOL is actually so smart that it will give you a molecule even if you don't have the best name. Does that make sense? Which is a little weird.
No, it just looks like almost completed honeycombs or something like that. Or when bees make those
It does. This one here, should I start numbering with this as 1? Is that the best numbering for this? No, because that way my first carbon branch would happen on carbon 1, 2, 3, 4, whereas if I number this way, 1, 2, 3, 4, 5, 6, 7, then the number's there. Why don't you take 2 minutes and you name this? And this one if you can. Yeah. Good for you, but hold off for a sec. But that's awesome. No, not right now. Actually, yes, if you can hit copier 2, those should be my next period's handouts printed out. Take it back. So give it a try and talk to each other. These ones I haven't tried to be sneaky. The main chain is just the flat chain. Same with this one. That is the main chain. So do just like we did here. Name your main chain. And then just find your side groups, right?
I have a question for second question, not that one.
Like this one here?
Yeah.
Yep.
The 3. Does it matter that like the chains, like one's above one's above?
No. Above and below doesn't matter because the truth is none of these are straight lines. If you go back to JMOL and look at how these end up being shaped, the 3-dimensional shape doesn't work in 90-degree angles. We'll talk about the angle it works in a little bit. But if these things because they're full of electrons and electrons repel each other, are trying to get as far away from each other as possible. And if you put 4 sticks into a ball and try to get them as far from each other as possible, 90 degrees isn't the best you can do. You can do better. This is a very specific angle. It's mathematically as far spread out as 4 spokes on a central hub can be in 3 dimensions. And it's an angle of 109.5 degrees. 109.5. And that gives us a shape that's called a tetrahedron. And the result is that there's no 90-degree lines here. That's why the skeleton diagrams always go up, down, up, down, up, down like that. But then you can see once you start throwing other groups in, it gets messy real quick, right? So the main chain here, hard to see. But that's okay. Thank you. Sorry?
We're doing practice tomorrow?
Yeah, oh, yeah.
Because our tournament's Thursday.
I know, I'm so
It's at Great Lakes, right?
Yeah, I'm so annoyed that we lost our second last practice.
I'm at least happier with how it is this year than last year, because last year was like right before exams.
Yeah.
Like right before.
Yeah, I wish it was like next Tuesday would be better, but that's fine. This will do.
Do you want to make a post about it?
Yeah, that'd be great.
If it's 2 stuff, it's
3. So 3 would be try. So if there's 2 of them, it would be, these are the prefixes you're used to. Die, that's right. In fact, not the worst thing for counting, and you'll never get too high with these. Mono, 2 is die, 3 is try. 4 is the one people forget. But think a game where they put 4 blocks together in all the possible shapes of 4 blocks. We call that game Tetris, because the prefix that means 4 is tetra. Don't distract me. 5 is penta, and we're not going to go higher than that, but let's put hexa in there while we're at it. So if you're counting and you need the prefixes, there they are. Okay, this main chain, what is it? It's 7. So what is the main part of this molecule? It's a heptane. Okay. What are these? These are both 1 carbon. It's 1 going up and 1 going down. So it's actually, they're both, this is a 1, 2, this is a 3 methyl. And what's this? That's also a 3 methyl. That's allowed. You can do that. If you can build it, it's allowed. And then what's this? A 4. Yeah, so a 4 ethyl. Good. So when you put this all together, alphabetically, what should come first? The ethyl or the methyl? Yeah, but alphabetically, do I start with ethyls or do I start with methyls? Just the alphabet. You guys know the alphabet. Ethyl. Good. So we start by saying 4 ethyl. And then I could say 3 methyl if I wanted to. But what's a better way to say it? 3. And then I need to say there's 2 of them. So I would say 2 ethyl. Dimethyl, right? Dimethyl. And then it is a heptane. Any spaces in there? No, because that is one word. 4-ethyl 3,3-dimethyl heptane. I'm not saying you should name your next cat 4-ethyl 3,3-dimethylheptane, the cat. But, and then, you know, if it has kids, you could name the next one 4-ethyl 3,3-dimethylheptane Jr. Be a good name for a cat, right? Right? That's a ring to it. That's all I'm saying.
You'd make the cat want.
It's like an Elon Musk naming system for kids. I read Walter Isaacson's biography of Elon Musk over the break, and I've read 2 biographies of Musk before, but Walter Isaacson is one of my favorite authors. He writes biographies of like kind of big figures in history. He wrote a great biography of Steve Jobs, great biography of Einstein, a great biography of Da Vinci. So I just read his Elon Musk biography. If anyone wants to borrow it, I'd be happy to lend to you. It's so good, so interesting. But it's amazing to me that somebody so impressive can also be so stupid sometimes. But he's a very impressive figure. But his children naming skills, I would argue, leave something to be desired. Anyway. Yeah. Anyway. Okay. Here we have a rule. Now, there is a rule that is less important but does matter. In this case, I could number these 1, 2, 3, 4, 5, 6, or I could label it 1, 2, 3, 4, 5, 6. Both are actually somewhat acceptable because in both cases, where do we get our first branch? Carbon 3. So here's the rule then. If it's going to work out that either way gives you the same number, give the lower like the alphabetical order. Basically, we're going to have the lower number come first in the name. Does that make sense? So in this case, if we number it 1, 2, 3, 4, 5, 6, the ethyl group will get the 3. And that's slightly better. I wouldn't mark you wrong if you labeled this the other way and called it 3-methyl. That's fine. What is our main chain here? It's 6, so that's a hexane. Good. And what is this group here? Yeah, specifically? That's a 3-ethyl. Good. And what is this group here? That's a 4-methyl. Good. Give me this as a name. Go. Who can do it? Keep going. Yep. Good. That's entirely correct, but it breaks one of our manners rules. In other words, somebody would absolutely know how to make that. It satisfies it. It's good, but what's better? Yeah, and why? We put the what we call the branches in alphabetical order. So give it to me again. 3-ethyl. 4-methyl. Oh. 4-methyl. Oh. Oh, I'm good. And then? Hexane. Good. All right. There we go. That's not so bad, is it? And I know like these names are long and they sound like they'd be really intimidating, but actually they're just like a little recipe in themselves, aren't they? They just tell you how to build this stuff. Organic chemistry is really interesting because if you can draw a shape made of carbon, hydrogen, oxygen, whatever, and it follows the rules, in other words, every carbon makes how many bonds? Yeah, and every hydrogen makes how many? 1. And if we're using oxygen, it wants to make how many? 2. And if we're using sulfur, it wants to make how many? Yeah, and nitrogen wants to make? And phosphorus wants to make? Yeah, if you build with those things and follow the rules, if you can draw it, it can be made in a lab somewhere. But the challenge is, where organic chemistry gets hard is how? How do you put these things together and say, I want to make this, not something else? And that's really complicated. We are very bad at this. Our cells are incredible at this, right? Our cells will like take sunlight and a bunch of carbon dioxide, and I mean, our cells won't, but plant cells will, and they'll make sugar over and over again. They'll make this big complicated molecule and they make the same shape every time. That's hard to do. You have to build little mechanical, little cellular machines. In fact, a lot of the time we try to manufacture chemicals, now we're developing new techniques where instead of trying to do it in a lab by sort of controlling the chemistry, sometimes we say, could we program a bacterium to make this molecule? And that's something we're learning to do, like insulin. Insulin, nobody's cracked the code of how to manufacture that in a lab. It's too big and complicated. Starting with just like carbon, hydrogen, and oxygen. So instead what we used to do is we used to slaughter animals, mostly sheep and pigs, and take their pancreases and take the insulin out of them. Then we'd give that to people to inject them. You might have some ethical problems with this. I have some ethical problems with this. Well, now what we've done is we don't do that anymore. Instead, we've programmed bacteria by putting DNA into them to make insulin for us. And you just get a big vat of these going and they will make it for you. It's pretty incredible. But in chemistry, in organic chemistry, they will sit down and say, okay, how do you make this? I had a professor at Brock, a raging a-hole. This guy named Dr. Thomas Hudlicki, T-Hud. He was the meanest human being I think I've ever met. All chemistry profs are intense. This guy was like, I think I'll ask Adam, ask him about him, but he was just a raging a-hole. Very impressive. But his whole thing was, he worked in pharmacological organic chemistry, and he held a bunch of patents for making like synthetic morphine derivatives. But here's the thing, you can't patent a molecule. So like when a drug company comes up with a drug, you cannot patent a molecule. Makes sense, right? Because molecules are fundamental things. What you can patent is a manufacturing method. Does that make sense? You can patent how you made it. So if you are a drug company and you come up with a new drug that does something, before you ever release it to the public, you hire a boatload of organic chemists and say, what are all the ways we could make this? And all the ones that are cheap and affordable and worth doing, you patent them so nobody else can do that. Does that make sense? So this guy, T-Hud, had worked out a bunch of patents on making like synthetic opioids and morphine derivatives, and was like richer than God. He was a maniac. I curl with the old head of the science department, the old chair of the sciences department, a guy named Jacques Mercier. He's a really funny old guy and a pretty good curler. But he tells me stories that Hudlicki, because he had all these patents and his lab was very prestigious, he was a Cantor Research Chair, so he was a very well-regarded scientist. And as a result, like he was just out of control. He said they had an explosion once in Hud's lab, because organic chemistry, you're dealing with a lot of volatile stuff. They had a full-on explosion. And luckily nobody was hurt, but like flames and fireball and like damage, like something exploded. And he said he went in and was like, so like, what are you going to do about this? And he's like, I'm going to set my lab back up and go. It's like, well, what's going to stop this from happening again? And he said, oh no, it'll happen again. That's fine. That's how this works. You deal with it once in a while. So scary guy, T-Hud. Anyway, we'll learn a little bit about how we do this. But now, as we know, carbon can make how many bonds? 4. And one of the things it can do is make more than one bond with itself. Does that make sense? We call that, if it makes 2 bonds with itself, we call 2 things that are connected by not 1 but 2 bonds. We say that bond is a double bond. Don't worry. Sorry, I should not have mentioned this. Don't worry about that. Just replace that word pi with double. We called the second bond. Just ignore that. I should have taken that out. I modified this note from my 4U chemistry, and I teach things in a slightly different order there. Don't worry about it. Just don't worry about that. Okay, so look here. If we have C to C, instead of making 1 bond, it makes 2. How many bonds can this carbon make now? 2 more for hydrogen, right? And this one? Okay, that would be C2H4. If we wanted to draw it as a chain diagram, we'd just draw it like that. We could also draw it as CH2, double bond, CH2. These are all acceptable. This is called ethene. But ene tells us there's a double bond. So we're going to lead off today, but this is good. Our timing is good. So if you see the suffix ene instead of ane, it's still a carbon chain, but it means that somewhere in there is a double bond. Now, ethene can just be called ethene because there's only one place to put the double bond. If there's only 2 carbons, where's the double bond go? Between them. Where else could you possibly put it, right? But what about this one? Well, if we have 3 carbons, there's actually 2 ways you could make that. All right? And in fact, I'm going to erase these and show it here. Because if we have 3 carbons, actually, no, there's not. If we have 4 carbons, let's do that. Now, the double bond could go here, but it could also go here. Does that make sense? By the way, it could also go here, but I'm going to argue that that's the same as it going here, because we would just start counting with 1 here. Does that make sense? But the important thing is these are different. Does that make sense? Now, how long are these chains? 1, 2, 3, 4, 1, 2, 3, 4. So these are both what type of group? 4 carbon? Butane. So this would become butene. Does that make sense? Ene tells us it's a double bond. But in this case, the double bond is on carbon 1, and on this case, the double bond starts on carbon 2. Does that make sense? So we would call this but, ready? 1-ene. We just changed the ending to ene, and we put a number in there to say where the double bond is. Does that make sense? So what would this one be called? But 2-ene. Does that make sense? That's all. So here the double bond starts on 1. Here the double bond starts on 2. So just before we go, because for homework you're going to finish this, but we're going to do the first one together. What would this thing be called? This one's very simple. How long's the chain? Yeah, okay, so it's a hex. All right, so it's a hexane, only it's not going to be ane because, you're right, here we have a double bond, and so this is an ene, and specifically it's an ene on carbon 1. We use the lowest number. Does that make sense? So altogether this would be called hex 1-ene. Not so bad, is it? All right. Now, what about when we have to put things together? No worries. This is still hex 1-ene, right? Does that make sense? So this whole chain, we know that this is hexane, but we know that because it has a double bond, we're going to call it hex 1-ene. But then, what is this group here? Well, it's coming down to a carbon. It's 1 carbon long, so what would that be called? Methyl group. And specifically, it is a 4-methyl group. By the way, when we're numbering, we would rather give a double bond a low number than a side chain a low number. That's one of those manners things. If you switched it and you gave this the lower number, I'd be fine with that. Though you still wouldn't do that this way because we wouldn't want the number to be 3 instead of 1, right? If we did it this way, the numbers would be 3 and 5. If we do it this way, the numbers are 1 and 4. So that's better. So, one sec, before you go, what's this thing called? 4-methyl hex 1-ene. All right, guys. It's not much, but I want that and these done for homework in tomorrow. Again, listen. Pound, pound, pound away this next couple of weeks, all right? Time to go. Yes, ma'am.